Everybody, welcome to the first virtual session at Simons Institute in Berkeley, and it's great to see everybody here. Many of you are here in person as well, and so you've already had a bit of an introduction to the Institute, but for those that are not, the Simons Institute is hosted by UC Berkeley and runs programs in theoretical computer science and also at topics at the intersection of theoretical computer science and other fields. And so this workshop that is taking place physically in Berkeley this week is focused on the economics of networks. And we have one fully virtual session, which has three fantastic speakers, Asu, who's here, and then we'll have a talk by Evan Sadler and then by Dean Eccles. And in between the physical and, in between the talks, there will be a half-hour coffee break where we will set it up so that people can come in the physical venue, talk to others, and in the virtual venue, talk to others. I encourage you to walk around and circulate and introduce yourself to others. You can sit at tables when you watch the talks and thereby chat with people at your same table. So yeah, this is an experiment of another way to do hybrid, and I appreciate everybody being game to try it out. So with that, I think we can get started with the technical content. Also, for people who are physically here after the last talk, I'll facilitate the lunch arrangements if you want to meet up with people for lunch. But in the meantime, let's start with the technical content. I'm very pleased to have Asu with us. It's fantastic that you were able to join us, and I think that's largely because we were able to make a virtual thing work out. So I love the fact that this hybrid format enables us to get great speakers that we might not see otherwise. And so I'm really excited to hear Asu's talk. She'll be talking about protecting privacy in new data markets. And so go ahead.
Thank you. Can you hear me, Nicole?
We can all hear you, yeah.
Okay, awesome. Thank you so much for having me. I would have loved to be there in person, but I'm so grateful you made this virtual option possible. It's such a terrible time of the term to travel, so this made it possible for me to be with you. And I'm super actually delighted that you're using this interesting platform, which I haven't used before, because I can see lots of people I know here. Oh my God, that's great to be with everyone. Today I'm going to talk about some recent work that we're excited about. As Nicole mentioned, this will be about data sharing, privacy protections in thinking about what kind of architectures should we be thinking about from equilibrium and optimality properties. So this is why it's recent work, a couple of different papers we're working on, and that's why I wanted to share our results with you today. It's joint work with Ali Raza Fallah. I hope he's here to take all the hard questions, as well as Ali Maktoumi and Azarak Malekian, phenomenal researchers. I'm super delighted that I'm working with them on this. And Daron also joined the team, Daron Asemoglu from economics. In the second part of the talk, I will talk about some even more recent work in which we are actually working with him on. So just as a quick motivation, if we look at online platforms, future of many services are intricately linked with consumer data. And this is very much driven by the advances in machine learning and AI, which have enabled huge promises in terms of, offering better services to consumers. Think about, more refined search results, personalized recommendations, informative ratings, and the list goes on and on. And of course, given this picture, the demand for data coming from corporations is increasing. And if you look at where this data is coming from, while some of it is collected from publicly available sources, census, or think about different surveys, American community surveys on demographics and so on, much of it is actually coming from users actually sharing their personal data while they're online on these online platforms. And this could sort of be in the form of, the data can be shared as a byproduct of other transactions, as what happens with Netflix and so on, or actually in exchange or free services that Google, Facebook, and others provide. But we're also seeing actually more and more explicit data markets. Nielsen here is, I think, a market and data measurement firm, and sort of this is becoming more and more of a reality. And if you look at sort of the trend, the use and transactions associated with individual data are almost certain to grow as these social media applications, new apps, new integrated technologies spread, but also as we keep using more and more services enabled by AI. And as I said, this is generally taking place automatically in your routine online presence, therefore creating myriad data externalities in terms of you sharing your data, but also making a lot of information available for other users. And this is the kind of data externality that I think Azarax will talk about in this workshop later on. But basically, all this makes privacy a very important component of all of these discussions as these markets are more becoming a reality. So there are some key questions that we want to sort of ask. Can platforms secure some amount of privacy to users while still collecting data? There's a lot of policy discussions around this question. So we would like to sort of think about what kind of systematic framework as quantitative people, computer scientists, can we provide some framework for thinking about these kinds of policy discussions? What kind of equilibrium privacy guarantees can we provide, and will these be sufficient from welfare optimality perspectives? And what are the architectures that actually emerge so that we can guide design of some of these markets as they shape up? So the setting is a simple one. We're going to think about a single platform and a group of agents who obtain utility from using this platform, and they share their data. And the data will involve a common component, be represented by some theta, random variable. And there's also going to be each user's own type. So theta will be basically some group-specific common elements. So think about how much group members value a service, or I think the best way I think about this is maybe it's a treatment for a medical condition that everyone will benefit from. So everyone has some data about, but everyone will benefit from. And the users also have some type that is more, individual information. Maybe it's irrelevant to their demand, maybe willingness to pay for services or type of ads that can be shown to this user. So both of these dimensions are useful for the platform, but the individual part could be costly for the users because they don't want this information about their own type be available to the platform. So that's sort of the privacy violation they will incur if they share their data. And the other aspect that I think is important to address, and we'll do so, is this privacy violation for individuals may vary across users. This is sort of, my data may be much less valuable than a more important, politicians' data. So there's a sort of different price sensitivities coming from different constituencies in the system. So I will, to address these questions, I will think about two relevant environments. These are two papers we've been working on. The first one will be basically, platforms can directly or indirectly, acquire payments for that data acquisitions. And this could happen when there's an explicit data market, or we could also think about some free services. So there's some compensation from the platform. So think about that being sort of the environment we're considering. In the second one, platforms do not pay for data, but they value this data collection that the platform engages in. This is the common component that they value. They will all benefit from a better estimate of that common component. And we're going to see basically what kind of architectures that would lead. And in terms of, a little bit going more into the two environments, the first one allows for explicit payments, and we will consider there essentially currently, common data architectures, in particular those that provide local and or centralized differential privacy guarantees. And we will have heterogeneous demands for privacy across users, and we will develop a mechanism design approach in which heterogeneous privacy guarantees are provided to the users. And this mechanism design, the mechanism will also output a differentially private optimal estimator as well as individual compensation scheme for the users. In the second environment, there are no payments. We will see, what kind of data architectures would be optimal, what are their optimality properties. And in particular, we're going to see that there's a well-defined class of stochastic mechanisms, in particular, a shuffling mechanism which shuffles the order of users' data before handing it to the platform that can provide the best privacy guarantee to users. But we will also see that even these mechanisms do not guarantee that platforms will actually stick with those user optimal mechanisms because of game theoretic interactions between the users and the platform. So some of this is going to come toward the end of the talk. I hope I can go all the way there. I have a lot as usual, but I will try to get into as many of the ideas that we're sort of currently playing with as possible. Okay, so something on related literature. There's a growing beautiful literature on this question of data acquisition from strategic privacy conscious users. I may be missing papers. If I'm doing so, please let me know. I recently started reading and I'm really, fascinating papers. In several of these papers, they use differential privacy to quantify the costs incurred, when sharing data. There's a number of papers in this area. The one that I would like to sort of highlight, it's sort of a very key paper is Ghosh and Roth, where there's some assumption indeed that there's some privacy conscious users, heterogeneous users, and then they design a mechanism to address a similar question. So there are some fundamental differences in that here they take a worst case view. There are no distributional assumptions on users' data or price sensitivities. And even though there are heterogeneous user demands, and they're interested in estimating the sum, of individuals' data. And those sort of assumptions together essentially amount to the mechanism providing single privacy guarantees. So it doesn't quite get into this notion of how do we do heterogeneous guarantees across users. It's a sort of a more dominant strategy type view as opposed to more Bayesian view that we're going to adopt. And there are other papers, some are new, and I think I'm missing one paper that I wanted to include here, but it's in our paper. But that actually consider the same question without differential privacy. So either, they're considering some menu of, allocation, price pairs, and an optimize over those. This is a very nice paper, Cummings, where they consider, purchasing data from users that provide different accuracies, different levels of accuracies for data, and strategically price that access to the data. So there's a bunch of things, and I think our paper is sort of different in the way that we're considering some optimal Bayesian mechanisms. We will see that that approach leads to different privacy levels for participating users. We're going to look at central and local architectures here. This is our sort of, I think, focus on what kind of architectures, and what are their properties. And then at the end, sort of we're going to deviate a little bit from differential privacy and say, without payment, what would user optimal architectures look like? And we're going to sort of try to see the implications of this shuffling, stochastic shuffling of user data, and what it would mean in a game theoretic environment. So that's sort of the landscape. Let me dive into the details. So the model is superbly simple. We have a platform. We have end users. The goal is to estimate some underlying parameter data. And each user has some individual data that's informative about that data. So data of user I is xi. Theta is the common parameter that we're trying to learn. And zi is some individual type that I was talking about. Let me use Ali Reza's favorite example. I think that's sort of very useful. So theta could be the effect of a drug, and zi could be the blood sugar level of an individual before the drug and after the drug. So you have access to xi, and you try to come up with some estimate of your theta by collecting this data from the users. Okay, so very sort of simple estimation setup. And as I mentioned, we're going to do sort of use differential privacy first to sort of formalize these privacy guarantees for user demand. The first one, let me start with central differential privacy. So this is, I view this as a worst case guarantee on the privacy demand of the user by limiting its impact on the output of the platform's estimation problem. Or more formally, you consider two data sets, S and S prime, which differ only in the ith component. Think about this as representing user I's data. And the definition essentially says that the impact of changing user ID data on the algorithm's output is bounded from above by e to the epsilon I. Okay, so there's an upper bound on how this particular user can impact the output. And I get always confused about what is epsilon I. So smaller epsilon I essentially means that user ID data has less impact on the output. Less impact means higher privacy guarantee or lower privacy loss. So thinking about epsilon parameter, it will be throughout our talk as the privacy loss level that the user is guaranteed. So algorithm A guarantees a maximum privacy loss level of epsilon I for user I. So that's central DP. So the next one is also, well, in the central case, basically the way we structure the DP is there's a platform, users trust the platform to share their data, only require a guarantee on the output, right? So the platform completely follows through with everything and we're guaranteeing something on the output. In the local setting, it's a sort of more stringent requirement. Users don't even trust the platform, and user I shares a completely private version of their data, which we denote by Ci of Xi. So this is a non-private input. We privatize each of the inputs separately and then feed it into the platform. And formally, we can actually guarantee that by just saying that an algorithm is locally differentially private if it takes these private inputs, private data as its input and has similar guarantee on the output. So it's basically, as you can see, a higher level of guarantee on the private input, and therefore, the immediate fact is that the locally differentially private algorithm is centrally differentially private. So it's basically more privacy guarantee provided by this local differential privacy. And a sort of common way of guaranteeing differential privacy is to add Laplace noise to individual, just add Laplace noise to your estimate or individual data, and let me call that Laplace noise or random variable has a distribution of this sort with some parameter eta. And if you think about, for instance, a linear estimator with this Laplace mechanism, it is in the form of take the user data, take a convex combination of their data, plus add noise, Laplace noise. And you can immediately see that if you do that, this is actually eta Wi centrally differentially private. I just wrote a very simple, this is maybe DP 101, but you can actually look at the output of the algorithm. You change Xi to Xi prime, and clearly the distribution of the Laplace by doing that changes by just this amount, Wi and Wxi. And then this is, if you do the cancellations, this is less than or equal to this. Oh, one thing I wanted to mention, sorry, this I forgot. I have an assumption on the noise or the individual type. I assume that they're zero mean and they're bounded. And people ask me what happens when it's unbounded. And I will there's a way to address that as well. So please ask Alireza or Azraq or Anali. So basically in this talk, we assume that they are truncated, they're bounded. So that allows us to bound this term by 1. And therefore, immediately you have this epsilon I or equal eta Wi guarantee on the privacy loss. So this is one way of guaranteeing this privacy by adding to your linear estimator some Laplace noise. Okay, so what I will do now is two parts in the first environment. So I will first show that there's multiple things here, right? We want to design an optimal estimator. We want to also figure out optimal ways of acquiring sensitive data or private data from the user. So the first part will be to figure out, suppose epsilons are given for fixed set of epsilons, what would be the optimal estimator in the environment that I just described? And I will argue that the linear estimators with the Laplace scheme are near optimal. And then in the second part, I will endogenize these epsilon i's. These are not fixed. We're going to ensure, right, that the individuals have this kind of privacy guarantees. I will endogenize by giving a utility function to each of the users. I will define what that utility function looks like, and then I will input that into a mechanism design problem and do that in both central and local settings. So that's sort of what we did in this first paper. So let me first quickly talk about, what do we mean by optimal estimators? And for that, we take the viewpoint of minimax optimality, which is used, quite a lot in the statistics literature. So we assume that epsilons, remember this is the privacy losses of these individuals, are known. And basically our goal is to estimate means of distributions. We take a family of distributions, and then we assume that this XI data are IID data drawn from these distributions, and we form an estimator using this data. And the question is, what is the optimal estimator? Well, we want to consider only estimators in this class of centrally differentially private estimators. So we need to optimize the error, and we think about the error as a worst case error, which is that, you look at the mean square error of this estimator. This is the mean square error. You take the worst case overall possible distributions, and you choose the best estimator against that worst case error. So this is the min max kind of, worst case error that we're trying to, optimize. And our first result essentially says that for distributions where you have this upper bound on your x, there is a lower bound on that min-max error. And moreover, there exists some centrally differentially private linear estimators that achieve that lower bound up to log n value. So this looks a little, I don't know, mathematically messy, but I just want to give you quickly how we actually go, because I think it's a very cool trick how you, come up with these lower bounds. I will just give you sort of the main idea of the proof. But before that, let me just mention that when all the epsilon i's are equal, like you don't have these heterogeneous sensitivities, everybody has equal epsilon, the lower bound reduces to a bound that was actually in Ducci as well as Dwork and Roth. And this is a typo. It's supposed to be a maximum. I was going to fix this, but I forgot. So it's basically the max. You can just put epsilon i's equal to some epsilon here. That will give you k square epsilon square, and the maximum is either at 0 or n, which gives you basically maximum of 1 over n or 1 over n square epsilon square. So that's our bound. And let me tell you how we got to this lower bound quickly. So the trick is to relate that lower bound problem to a hypothesis testing problem. And I hope I don't lose people here because but it's actually, it's a cool trick. So I will go over it. But if you get lost, I'm happy to come back to that to talk about it. It's not super key, but anyway, so essentially, remember we were trying to lower bound the minimum overall estimators, the supremum of the error, right? So since it's the minimum, it suffices to show that for any estimator, you have the lower bound. And then this is over the maximum overall distributions. I picked two distributions, P1 and P2. This is the P1 and P2 and their mean. And I call gamma the difference between their means, 2 gamma, the difference between their means. So this is for a particular distribution. Okay, so instead of the supremum overall distributions, I lower bounded by the average of these error in these two distributions. Okay, and this is the average of the mean square error, theta hat minus theta for that PJ, for that particular distribution. I simplify this by, instead of thinking about the distribution on the data xi, call y to be the distribution on the estimator, theta hat. So then this is equal to, over that q, y minus theta pj. I did nothing here. I just said p is the distribution on data, q is the corresponding distribution for the estimator. And this is sort of again, the mean square error. I use a Markov inequality to say that this is bounded from below by the probability of y minus theta being greater than equal to gamma. And then basically you can view this probability as a probability of error for a nearest neighbor classifier. So you can ask the following question: given some means, given some realization, theta hat, is it coming from theta P1 or is it coming from theta P2? So if it's, gamma close to 1, it's going to come from here, gamma close to 1. So it's the nearest neighbor type of argument. But you can show that the error for this kind of, question, hypothesis testing question, is given by the error probability of, coming from one versus the other distribution. Okay, so that's sort of the first step of getting from here to this kind of error probability for some hypothesis testing problem of this sort. And then there's a beautiful method from statistics, Lecan's method, that actually lower bounds such error probability by a distribution distance on Q1 and Q2, TV distance, okay? And so far, actually, what I've been talking about are classical tricks to get lower bounds. I think the main, contribution in the paper is to actually show that when you have differential privacy kind of constraints, you can put a distance on these distributions by two terms. Part of the term is coming from differential privacy and the TV distance on P1 and P2, and part of it comes from data stochasticity and comes from a KL divergence between those two distributions. So basically, we sort of identify two sources of stochasticity, some coming from differential privacy, some coming from data stochasticity, and enable that to come up with a refined bound on this distribution difference. And then remember, I chose P1 and P2 to be arbitrary distributions. I choose them as specific Bernoulli distributions. That gives me this upper bound for those particular P1 and P2. Now I can put this back in my lower bound. You will get something in terms of gamma, which was another free parameter. And basically optimizing over gamma gives you the lower bound that I have presented before, okay? So sort of a couple of steps, but I think a cool technique to come up with lower bounds on such min-max error terms when you're thinking about optimal estimators. So this was just for the lower bound. And now for the upper bound, or sorry, for the achievability result, we basically said, remember that a linear estimator of this sort achieves central differentially private, but also achieves optimality. And essentially that comes from, I will go into a little bit more now, but the bound, remember, was this max of this kind of thing with a K ranging from 0 to N. You can write this for a particular K star as the minimum of 1 over N minus K star and 1 over this particular term here. And then basically then this is the lower bound. And the rest essentially of achievability comes from figuring out that if you think about all of your data, x1 to xn, the first part, x1 to xk star, you can actually make them differentially private by setting the weights wi eta to equal to epsilon I. And you can show that that contributes exactly to this error. And then this part basically comes from, setting the rest to data stochasticity. So you set the rest equal to, all these weights equal, and they contribute a term of 1 over N minus K star to your error level. And then you need to choose K star in a way that, there are two error terms, remember, coming from differential privacy and data stochasticity. There's some point of K star at which one of them starts dominating the other one. So you choose K star to exactly figure out where one is, more influential than the other error. And that gives you essentially exactly this lower bound, showing that this kind of linear estimator achieves that lower bound. So I hope this was clear. I can't see everyone to be able to go over wherever might not be clear, but this is just to give you an idea of how this could be proved. And you can use similar arguments. I don't want to go into the detail, but in the case of local differential privacy, you can show that similar arguments, linear estimator with Laplace mechanism indeed is also min-max optimal in this setting. So once we achieve that, these linear estimators are min-max optimal, I will now go into the mechanism design problem. Remember, so far, I just said epsilons are, exogenously given. I'm going to endogenize them. To do that, I will basically say that each user has a type CI, which represents his or her privacy sensitivity. This is per unit cost of privacy loss for user I. I'm going to assume that each CI is independently drawn from some distribution Fi. And I will say that all of this CI is the C vector. So this is the vector of privacy sensitivities. And I will consider a mechanism where individuals participate by sharing their data and reporting their privacy sensitivity. So there's an assumption I'm making here. I assume that users can lie about their privacy sensitivity. They can say that I actually care a lot about privacy. That's something they strategically lie about. But we assume that they cannot manipulate their data. So this is basically an assumption that will hold, for instance, if the platform is the one that's actually collecting the data. So as long as you participate, your data is scooped, or it can be verified somehow. It would be interesting to see, if that could also be manipulated for, this kind of utility construction, but that's not what we do in this paper. And then depending on the reported sensitivities, platform provides a compensation for the user, which is TI, and that's a function of the entire reported privacy sensitivities. And then mechanism spits out privacy loss levels as well as differentially private estimator. Okay, so that's our mechanism. Basically, you have this data XI, you have this CI. So as I said before in the beginning, comparing to other papers in the literature, we're making distributional assumptions here. And then user reports CI to be the CI prime, that's his report. And then also shares the data XI or XI hat, depending on whether it's a central or local architecture, and the mechanism outputs all of these things that I already mentioned. Okay, so let's go now to write down first the cost function. So again, user shares the data with the platform. That's a benefit he gets, right, by leading to a lower estimation error on the common part, but incur a privacy cost because there's going to be some leakage of privacy. And we define cost instead of utility. That's easier to work with. And we basically say from the participation, there's some mean square error that you incur coming from the common part. And then you have some privacy cost, which is your type, actual type, CI, not your report. That's how much you incur, that's the actual type. And then the privacy loss that will be output by the mechanism, which is a function of your report, CI prime, minus the compensation you receive. Note we're doing cost, so we just turned it into a minus compensation. And then the mean square error is basically exactly the estimator minus theta. And note I also put here dependencies on CI prime and C minus I because the epsilon that the mechanism outputs depend on these CI prime and C minus I. And then if you don't participate in the mechanism, you have nothing, just your own data. So your best estimate, given your data alone, is just your variance, xi minus theta. This is the variance of the noise. So that's will essentially dictate your participation constraints. Okay, so this is cost function. And the mechanism design problem is the platform will minimize an objective function, which is given by mean square plus total payments it makes to all the users. There's a revelation principle here. I'm actually going over a lot of things, assuming some knowledge background in mechanism design, but basically you can just assume that a direct revelation mechanism where individuals report their type truthfully is a Bayesian-Nash equilibrium. And this is without loss of generality. We can constrain ourselves to mechanisms of this sort, and we formalize this by imposing an incentive compatibility constraint, ensuring that truthful reporting is the Bayesian-Nash equilibrium, and then individual rationality constraints, making sure that platforms does not make users worse off by participating. So the mechanism design problem then is minimize this objective function of the platform subject to IC constraints for users. Each user is better off reporting his truthful type while others are reporting correctly. And also his cost for participating is less than or equal to his outside option. Okay, so very, what is the word, innocent looking problem, except that it's highly non-convex, it's infinite dimensional. We need to minimize over all possible estimators, all possible privacy levels we guarantee, as well as all possible payments. Anyway, but I think the analysis is actually has a lot of similarities to Meyerson's seminal work. Basically, we first figure out sort of some characterization on optimal payments, optimal interim payments, by using the first order optimality conditions of this problem. You just say that the payments, optimal payments, need to take this form as a function of epsilon. So this is a trick, right? You try to reduce the dimension of your optimization problem. First, you get rid of the payments. You write everything in terms of epsilons for any estimator. And then you plug this back into your optimization problem. There's some free parameter here, which is, it's a free parameter for all optimal payments, but because you're looking for the optimal mechanism, of course, you want to minimize that. So you set that equal to 0. So then you put everything together and rewrite things in terms of some virtual costs. This is also, for those who know Meyerson, will look familiar, not the same, but familiar. And then, we get rid of the payments this way. This becomes only a minimization in epsilons now and the optimal estimator. And then we assume virtual cost is increasing. Again, this is similar to Meyerson's, monotonicity condition. But once we do that, then we basically focus on linear estimators here from now on. And for a linear estimator, for central differential private, I'm going to assume this linear plus Laplace noise, and I will write the mean square error corresponding to such an estimator. That simplifies my problem even further. Okay, so that's the problem that you need to solve to be able to figure out all of these parameters now. The problem is it's still non-convex. So unlike Meyerson now, it's still a nasty problem because you have also estimators and stuff. But I mean, these guys are amazing in dealing with the nasty problems. You can just show that this can be solved efficiently. It has beautiful structure in it that it can actually be solved efficiently in time and log n. So I hope this approach is clear. And then, you can do the same thing with local mechanisms. You just have a different mean square error. You plug that back in. And in this case, we weren't able to get efficient guarantees for the exact solution, but you can come up with an epsilon approximate solution in polynomial time in n and 1 over epsilon. So, okay, so that's essentially algorithmic characterization of these two architectures. And then one can ask the question of what do platforms and users prefer? And okay, I'm running out of time badly. So I will just say that, from the platform's perspective, you can look at, which of the architectures gives better objective function value for the platform. It turns out central differential privacy does that. And it's not too, it's actually intuitive because if you think about it, local differentially private estimator is more stringent, gives more stringent guarantees. So platform actually can use a central differential private architecture to get a better mean square error and payments using a central differential architecture. And for users, you can do some nice comparative statics and see that depending on their privacy sensitivity, they may prefer central versus local architectures, and different users may have different preferences for doing so. I think there's much more to do here in terms of comparing these architectures and seeing sort of from platform and user perspective, which ones are preferred. Happy to discuss that more offline. So
just a heads up, you have 5 minutes left.
Okay, I was going to talk about another paper. Okay, that won't happen, but I will try to maybe tell you a little bit about what this is about. So far, everything was in terms of differential privacy, right? I fixed the differential privacy guarantees. That gave me optimal estimators in terms of central and local differential private estimators. So it's important, I think, going forward to understand what other data architectures could provide optimality properties and in what forms. So to study that, we will actually think about a different game theoretic environment now, in which users can actually decide not to share their data. Remember, in the previous model, they were able to do that through their participation in the mechanism. This is without an explicit prices or mechanism design. This is a choice we give to the users. I will use a different metric for value of data, and that's called revealed information. And in our group, at least, we have very heated discussions on whether that's the right notion or differential privacy is the right notion to think about, while thinking about design of data architectures. I will just make a maybe comment that while differential privacy has been great, it really provides this worst case upper bound type guarantees. So if you're thinking about game theoretic analysis where you need to write utility functions and where you're trying to provide optimal data architectures, the upper bounding arguments don't bode very well. So this is the reason why we actually went and started thinking about a different notion for leakage of privacy. And I will hopefully tell you at least what that is. And then I will try to show you the user optimal data architecture using this kind of, and then there's no explicit prices. So that's essentially trying to capture the fact that right now on many platforms, there's still limits on what kind of explicit payments you can provide to the users. Okay, so given that, then let me just tell you maybe 2-3 things and then wrap up key things. So the first one is this revealed information notion. Remember, the model we had was exactly theta plus di. Each data has a common component and the private component. Revealed information is, we took mean square error, there could be other things, is basically the reduction in mean square error before and after observing the mechanism's output. So you have some variance on your theta. This is how much you know about theta, right? You can think about it ex ante without seeing anything from this platform or from this mechanism. You put it through some mechanism and you learn things about theta. And basically, this is how much you learn. So this is the revealed information because you have this mechanism. And you can also define ZI revealed information about the private types very similarly using this ex ante and ex post distributional approach as opposed to this worst case DP approach. So that's how we define revealed information. And the other thing I want to define is a shuffling mechanism. This is also just to contrast it with this differential privacy where you're adding noise, right? This is a different way of adding noise. And I think in a game theoretic environment, at least in the first, modeling sense, it makes sense. So we have users and each user decides to share their data or not with some probability QI. So this is their decision, QI. And then you turn it into, you input all of this decisions into a shuffler, which actually takes a permutation or shuffles the order of the data. And we call that sigma 1 to sigma n. And that's what is given to the platform. Okay, so this is a particular mechanism that takes the user input and turns it into, what you're going to feed into the platform. And one thing that I put here in red is we assume in this particular mechanism that all of the data is shuffled, even if, some of them are not shared, but, you have something and you can't look into it. The shuffler just shuffles everything, even though some of them may be empty. It doesn't contain user data. I'm defining this because I'll say this is the optimal one from user perspective. So essentially that's the first result, which says that this full shuffling mechanism that I just described is user optimal, and that's in quotes because that's in a Pareto optimal sense, in the sense that for any mechanism, there's an inevitable leakage of privacy information that is bounded from below by how much you can learn about the common part of the data. And that's sort of this line exactly in this space of privacy cost and level of learning. And moreover, the full shuffling mechanism achieves this Pareto boundary by thinking about Q1 to Qn equal to some Q, and each Q achieves a different point in that region. So that's the optimal. I will skip the proof. Now I'm going to put this into a completely game theoretic environment in the sense that I will also give some agency to the platform. I will assume that platform now has a parameter which actually it decides. This is its shuffling parameter. It commits to shuffle each user's data with probability mu. So it says, given the yi, I will shuffle it with probability mu, and I will not shuffle it, and I will immediately get it with a probability 1 minus mu. So this, if you think about extreme cases, if mu is, for instance, 0, that means I'm not going to shuffle your data at all. I'm going to take it as is, right? So this is actually a privacy guarantee that the platform promises to the users. And then knowing this mu, users decide on whether or not they're going to share their data. So it's a two-stage game. Platform chooses mu, users chooses whether or not they're going to share their data. And then I'm going to do the same thing as I did before. I'm going to, give some utilities for the users. This is going to be the utility of revealed information about common component minus this utility of, revealed information about your private type, and platform values both components. And we put some parameter delta about how much it values theta versus di and so on. And then I'm not going to define it, but we define a Nash user equilibrium given the mu's, and then Stackelberg equilibrium for the platform to optimize over mu. And then you can do interesting things with this equilibrium. In particular, you can show that actually at equilibrium, as the users this is just a characterization of the equilibrium. So you can do a characterization of the Stackelberg equilibrium in that, you look at the alpha parameter, which is how much users care about learning. And there's some alpha bar and alpha upper bar such that below that, the Stackelberg equilibrium is to provide full privacy guarantee, and above that to provide no guarantee. And in between, this is just some, this is not linear actually, it's just a cartoon. It's just decreasing in some manner from 1 to 0. So that's how the Stackelberg equilibrium looks. And then, there's very weird paradoxical things happening in this equilibrium. Essentially, one that I will highlight quickly and then wrap up after that is that, as alpha increases, as users care more about learning, their utility should increase, right? Keeping the platform's action fixed. If the platform is using the same action, that gives the same equilibrium. And as alpha increases, utility increases. But it turns out that in equilibrium, as users care more about this common data, actually the overall platform equilibrium makes user utility worse off. And that can be seen by actually this characterization of the equilibrium in that, when alpha increases, the privacy cost, this privacy cost that the platform is extracting from the users abruptly decreases. And even though users gain more from learning, because platform is exploiting this, it actually extracts much more privacy loss from the users and therefore making their overall utility worse off. And then I will not talk about this because it will take me another 5 minutes. Basically, we started also asking the question of when do platforms deviate from user optimal architecture? This kind of taking advantage of privacy losses of users actually makes the platform deviate from this user optimal architectures and do things that make users significantly worse off compared to what their optimal would be in equilibrium. And I think this is a very interesting area to think about what data architectures actually create tensions between, platform and user viewpoints, and how can we think about, not using those that further empower platforms when we're thinking about, getting the benefit of learning, yet, thinking about all these privacy costs at the same time. Anyway, I will conclude, and I'm hopefully not too much over time. So the goal was to think about design of mechanisms for acquiring data from privacy conscious users who also, benefit from this data sharing. So there's this tension between data sharing and privacy. We considered two setups with explicit payments and no payments and try to think about optimal architectures. And I think there's a lot that I feel our community can think about. That's why I wanted to share this work, thinking about how to design incentives, how to trade off multiple performance metrics. Can we think about different learning objectives than just the linear estimation problem? Can we think about more nuanced models that takes us beyond differential privacy? And what other performance metrics can we think about in these kinds of situations? So with that, maybe I'll stop and see if there are questions.
Thanks so much. That was a fantastic talk. People in the room, you can clap with a little avatar, or you could clap if you're in a physical room with your hands. We have some time for questions if Asu does. And
as long as I don't disrupt the program.
Please do either navigate to a mic. You can also, if you stop screen sharing, people can then walk around. And then you can navigate to a mic to ask a question. If you're in the physical room, you can also ask a question with these microphones. So
I had a question. So the model seems to assume that the user data is IID. If the user data is not IID, then differential privacy is no longer kind of a worst case compared to the variance, the revealed, I can't remember what you called it.
I only heard not IID.
Say that again.
I only heard your part of your question.
Maybe you should come in front of the laptop.
Oh.
Hello, I'm sorry. Yeah.
So it seems like you're making this assumption that the user data is kind of IID, or the noise is IID.
Yep.
And if that's not true, then differential privacy doesn't provide an upper bound anymore compared to in the state of this revealed, I can't remember called, or the revealed information, because the correlations between agents can reveal more information about a person than is differentially is accorded in differential privacy. So I was just wondering if you had thought about that tension at all and where the future direction is.
That's a fantastic question. We have thought about it, but we haven't done anything about it. I think the fact that your privacy sensitivity depends on the data you're sharing, is a very natural correlation that one should think about in these kinds of models. We haven't done anything about that yet. We would like to. I think this revealed information setup provides, a natural framework for thinking about perhaps that kind of correlation. My answer is I don't know the answer. We haven't done it, but I think that studying that kind of correlation, what kind of preferences that would lead from user perspective, from platform perspective, would be very interesting to study. And I would do it in the revealed information framework, because that allows us, I think, to be able to work with those correlations. And Azar I think will talk a little bit. It's not correlation between data and privacy, but Azar will talk about some of the correlations between data externalities in her talk. I think, so it's possible to use this kind of framework to address that question, and it would be very interesting to do so.
Awesome. Kevin, you can unmute and ask your question.
Question about the second paper you presented. So if I understand correctly there, the IR constraint represents if someone opts out, then they do not have access to this like estimate that gets, produced. And if someone opts in, then, I send them the thing, so that reduces their error, right?
Yeah.
So I'm wondering, in that context, instead of paying users different amounts based on the reports, can you then, instead of that, use like different kinds of like information design tricks, or like I send you more distorted estimates, or vary the quality of the estimate I send you, instead of using like the monetary payment dimension to ensure, like, would that be a cheaper way to do things?
Possibly. I don't know if it's going to be cheaper, but that's actually a very interesting idea. Instead of payment, one can think about, providing different levels of accuracy on the common component.
Yes, I mean, if you're already able to do that for someone who opts out, that is shut off the information completely, then of course you can also vary the quality.
It feels to me like the Cummings paper, kind of, which I loved reading, thinking about providing different levels of accuracy. That would be very interesting to try out.
Awesome, thank you. I think if there are any other questions, maybe you can type them in the chat. Ali and Azarash are both online, so they can definitely answer questions. And also, if you want to stick around, we're going to have a break after Evan's talk, and people can walk up to you individually in the auditorium to ask questions. So
wonderful. Thank you so much. Thank you, Nicole. Great to see you all. Hopefully in person soon.
This was a lot of fun. Thanks.
Thank you. Thank you. Bye-bye.
Bye. So Evan, you can walk up to the podium, and